Now, let's work on obtaining the equations of motion. There are two different ways that you can obtain the equations of motion using typical dynamics approach, like applying Newton's methods. So Newton-Euler equation, what you have learned in your dynamics course in your undergrad. So first step is define the reference coordinate, draw a free body diagram, and just formulate the force and motion relationship of the free body diagram into mathematical formulation. Okay, like F equals ma or torque equals I alpha. Another way is to use the Lagrange's equations. It is a different compared to the Newton's Euler methods. The difference is it's a scalar analysis. So the detail more in details will be explained in the later session, but I'm going to briefly go over the steps. So first you should generalize the coordinates. Okay, so coordinate Q, generalized coordinate is similar to the typical coordinate what we have covered so far, but the number, it's a kind of minimum number to be required to describe the motion. So sometimes your Cartesian coordinate x and y's are mutually dependent, or something like polar coordinate with r equals constant. Then your generalized coordinate number is going to be less than a regular coordinate number. We're going to study about this later. Once you set the generalized coordinate, then you should formulate the kinetic energy, potential energy, and generalized force. So with the kinetic energy and potential energy, you can define the Lagrangian L, which is T minus V, and take a derivative like to formulate the equations of motion. So those are the steps used for obtaining equations of motion using Lagrange's method. First, let's work on using Newton-Euler equation. The very first step is to set the coordinate to describe the kinematics, right? And then you should actually figure that out what are the forces applied to the body. So to do so, we should draw the free body diagram. The free means of detach, okay, here. Detach the body from the all its environment, including ground or to the other bodies, and just draw all the forces applied to it. And then note that all the contacts exert the forces, plus the field force like gravity or magnetic force or electric force. But for the Newtonian method dynamics, mostly the gravity. So for example, suppose that human walks, okay, to walk, human requires a proportional force. Those are generated by the muscle force of each joints, like hip joint, knee joint, and ankle joints. That will actually generate the rotational motion of the foot that will actually push the ground. However, if you want to draw the free body diagram, you have to figure that out the forces applied to the body. So free the body, free the human, okay? So you only have a contact point, stigma of a contact point with the ground, okay? Then the force is applied through the contact. So there is a ground reaction force applied to the foot, the ground contact point here. And the field force gravity, that's it. That's the free body diagram of human walking. Suppose you want to draw a free body diagram, and then to generally express the forces applied to the contact point, whenever you cannot specify the direction, you can generally split it out in x and y components or friction and normal components here. Now, suppose that you want to draw a free body diagram when you are making a model of the point mass and massless legs, like this setup. Okay, in this case, once you free the body part here, then just detach it from all the other environment or the other bodies, then this is a point mass alone, right? In this case, how would you draw the force and its direction? That lies to the analysis for the leg first. Okay, for the leg, if you free the leg, okay, this is a free body diagram of the leg. There are contact point with one here with a large point mass, and there is another contact point here with the ground or the small mass, right? So there are two forces applied to the system, so which is F1 and which is F2, okay? And with this force, you can obtain the equations of motion, Newton-Euler equation here. So here's a vector formation like F1 minus F2 or plus whatever, is going to be MA. And moment equation with respect to say point O here, it's going to be L cross product F1 is going to be I alpha, right? However, suppose that this one is a leg with mass is negligible. So it's massless leg. That means this term goes out to be 0 and inertia term goes out to be 0. So what that means is whatever the force is applied to the massless system, those forces should be equal in magnitude and opposite in direction. Okay? So maybe this, if the magnitude of this green arrows are same as the magnitude of the green arrow here, yeah, that does make sense. Same magnitude and opposite direction. For the moment equation here, so if this L cross product F1 turns out to be 0, what that means? Since L is not going to be 0, what that means is F is going to be 0, but that's a trivial case. Or the cross product will be 0 means that the only force applied here should be along the leg direction, right? In that case, L cross product F turned out to be 0, right? So what that means, since your Newton's law, second equation F equals ma, should be 0. So what that means is this F2 should be also aligned through the leg, right? So whenever you have a massless body components, you can assume that the forces are applied along the massless leg. Okay, so those are the direction for to apply the force applied to the mass and to the foot mass as well. Okay, so here, remember at the contact point, we only draw the forces. How about the torque? Is the ground reaction torque could be applied? Well, depending on how you model this contact point. If you have a contact point as a point mass, point foot, then torque cannot be held, so the torque is going to be 0. But if you have a surface contact, like a human being, like a human has a foot has a surface contact, then there is a distributed load applied, and then you can actually calculate equivalent torque. So depending on how you define the contact point, you can either assume there is a torque applied at the contact point or not. Okay, so with that, let's obtain the Newton's Euler equation for the human body in walking case. So when you have a double support phase structure, it looks like there are many rigid body components could be used to model the human posture, walking posture. So to draw the free body diagram, first step is you should free the body, right? So you should detach the body from this environment or adjacent body segment. So suppose that this is the foot, this is the shank, and this is the thigh. Now, the first step is to set the reference coordinate frame. So I'm going to set the reference at the ground, or somebody might to set the coordinate at the center of mass. Yes, why not? And somebody might set the contact point at the hinge point, which is connecting to the other one. Either one is okay. So depending on where you put the reference frame, just stick to it coherently. Okay. And suppose those are not massless. So it has an inertia term. That means there's a torque could be applied. So generally, suppose that this is a point contact. The foot has a ground point contact. So only force is applied at the ground, but for the shank joint components, there are force as well as a torques. And there is also gravity is this ignored here. So same things apply for the next segment. So there are from foot segment there is action reaction pair. So same magnitude opposite direction pair at this point, and there is another force and torques applied from the next segment. For the next segment, this is also action reaction pair, and also there is another joint force and joint torques applied. And once you draw the free body diagram, you can obtain the equations of motion from Newton-Euler equation, like all the forces are equivalent to the linear momentum change, and also torques are equivalent to the angular momentum change. Okay, so then let's go a step further at modeling this one. So I'm going to set the reference frame at the ground contact, and the forces are contact point and from the next segment's hinge joint, there I have a internal force applied, and well, which is considered to be external force once I free the body as at the foot, and torque, and also gravity. To formulate it, I'm going to define the geometry parameters here from the contact point to the ground center mass. That the distance will be rho a with the theta angle theta, and the contact point to the from the reference frame is going to be defined as L. Okay, then I can obtain the equations of motion. Here the forces are three, F1 and F2 and mg, and the torques with respect to contact point O is three. One is with the gravity, and the other is a torque, and the other is contact force, joint force from the second segment, L cross product F2, which is going to be IO theta double dot. Now, can I obtain the moment equation with respect to G? Yes, of course. So in that case, you have a force component generating torque, which is F1, F2, and tau 1. So F1 rho, in this case, from center of mass to this point is going to be minus rho cross product F plus tau 1. And from center of mass to this contact point, it's going to be L minus rho cross product F2. Okay, so and then which point you set it as a reference point, the torque equations should be equivalent. Now, working on the second segment, which is a shank, I'm going to set the reference frame at the hinge joint, and all the forces are here F2 and this one is action reaction pair. Okay, one is action reaction pair. And there's a gravity and there's another force applied at the hinge, next hinge, and the torque. And then also geometry components like a rho, theta, and L. So three forces applied to generate the F equals ma, and torque components with respect to the P here is going to be by the gravity and tau 1 and tau 2 and L cross F3. However, there is one thing to note, that is for the shank. I mean, if you set the reference point at P, which is anchor joint is moving with the acceleration, right? So what you have to consider is the inertial force. Yes, because this currently set it reference frame at the ankle joint is non-Newtonian frame. So acceleration at ankle joint P should be applied as a form of inertial force at the center of mass with the magnitude of MAP, directing opposite to this acceleration here. So here, when the reference frame is set to an accelerating point, like a non-Newtonian frame, consider inertial force is applied where? At the center of mass with the magnitude of m multiplied by the acceleration. Minus sign here means the opposite direction. So here, the inertial force is missing here, and there is the torque by the inertial force is missing here. So you should add them to actually complete the equations of motion. Now, in the second segment of the shank, can I still obtain the torque equation with respect to the center of mass G? Yes, of course. So in this case, you only have four torque components by the F2 and F3 and tau 1 and tau 2. Since you set the reference point as center of mass, you don't have to consider about the torque components by the MAP, the inertial force. So whichever simpler you can choose to obtain the equations of motion. And note that those are equivalent anyway.